Assalamualaikum and good afternoon everyone. So today we will continue on the methods of evaluating estimator. So we already looked at the concept unbiased estimator and so on. Okay, we already solved. Then we proceed with the finding the variance of point estimator. So where we use the Kramer-Rao inequality. So if we recap back definition of unbiased estimator, so any statistic whose mathematical expectation is equal to a parameter data is called as unbiased estimator of the parameter data, where you can write down expected value of U is equals to data. Otherwise, the statistic is said to be biased. So the bias of a point estimator U, you can write down as the difference between the expected value of U minus theta. The difference between expected value of U and theta, which is expected value of U minus theta, is called as bias. Okay, let's say we refer to the first example, example 1. So this one is a uniform distribution, 1 over theta. So the range is 0 less than x less than or equals to theta. We already solved this one. We find that MLE of theta head is just the largest ordered statistic. Okay, so now we want to verify whether we have unbiased estimator of theta or not. So again, we need to find what is the PDF of the largest ordered statistic. So the PDF of the largest ordered statistic, if you recall back on mathematical statistic, so it just gives us as Fyn theta, which is n capital Fyn to the power n minus 1 times the density function small Fyn. So capital F is your CDF. Okay. So over the range A less than Yn less than B. So first you need to find what is your capital F. So F x theta. So we need to integrate 1 over theta dt. So from 0 up to x. Okay. Solve this one. You find x over theta. So let's say we denote as the largest order statistic as y. Okay, we use different variable which is y. So that's mean Fy theta is just n. Okay, this one capital F y over theta to the power n minus 1. Fyn small f, which is your density function, 1 over theta. So simplify, you just write down n over theta n, y to the power n minus 1 over the range 0 less than Yn less than or equals to theta. So again, you want to find the unbiased estimator. So use the concept of expected value of y. So expected value of y times the density function of your ordered statistic. Okay, simplify n over theta n. So you just integrate y to the power n. Solve, you will get y to the power n plus 1 over n plus 1. We substitute 0 theta. So last you get n theta over n plus 1, which is not equals to theta. So in this case, your Sn is a biased estimator. So the property of unbiasedness is not in general property of MLE. MLE can be biased or unbiased. But again, how you want to determine whether your theta head is a good estimator. So it must be unbiased estimator, efficient estimator, and also consistent estimator. So we go to the concept of efficient estimator. So we already discussed this before. So y is unbiased estimator. So the statistic y is called as efficient estimator of theta if and only if the variance y attains the Kramer-Rao lower bound. So that means since we know that CRLB is the smallest value that the variance of any estimator can be, so the efficiency of an estimator of theta can be assessed by comparing its variance against the Kramer-Rao lower bound. Okay. So now we refer back to the first example. We already found theta head is the largest ordered statistic. So we already found expected value of y is equal to n theta over n plus 1. So how to make it as unbiased? So since n over n plus 1 is a constant, so you can write down expected value n plus 1 over n y is equal to theta. So n plus 1 over n y is the unbiased estimator of theta, not y. Unbiased estimator of theta is n plus 1 over n y. So to find whether this one is efficient estimator or not, so we need to find the variance. So the variance of n plus 1 over ny. So use the properties of variance, you will get n plus 1 over n square variance y. So variance y is just expected value of y square minus ay square. So you solve this one first. So finding the variance, ay square minus ay squared, the value. So expected value of y square. So since the PDF is the largest of the statistic, so again we substitute y square times the PDF function and y to the power n minus 1 over theta n. So integrate from 0 up to theta. So solve n over theta n. Integrate y to the power n plus 1. So you will get y to the power n plus 2 over n plus 2. So substitute the value 0 theta. So in this case, we will get substitute theta n theta square over n plus 2. Okay. So you need to find what is your variance y. So again, substitute ey square minus ey squared the value. So we have n theta square over n plus 2 minus n theta over n plus 1 squared. Okay. So what you want to find is variance n plus 1 over n y. So again, the properties n plus 1 over n squared variance y. So this one, time this one, simplify, expand and simplify. You will get variance theta head is theta square over n plus 2. Okay. The second, you need to find what is your Kramer-Rao lower bound. We need to compare variance theta head with the Kramer-Rao lower bound. So we proceed the Kramer-Rao lower bound. So since your PDF is just fx theta 1 over theta, so you take ln, differentiate ln. Okay, so you have minus 1 over theta. Okay, so that's when differentiate minus 1 theta is just minus 1 over theta lah. Okay, so again, you square the value, differentiate ln fx theta over d theta and then squared, you will get 1 over theta square. So use the method for Kramer-Rao lower bound. So you will have n expected value d ln fx theta over d theta squared. Okay. And then bracket to the power minus 1. So again, you have n over theta square to the power minus 1. So the answer of your Kramer-Rao lower bound is theta square over n. So now we compare the various theta head that we already get before, which is theta square over n plus 2. Okay, so let's say we get various theta head. So variance theta head you get before is theta square over n plus 2. So you want to compare with your Kramer-Rao lower bound theta square over n, which is your CRLB. So is it theta square over n plus 2 is not equal to theta square over n? Is it larger or is it smaller than? So let's say we choose, let's say your n is equal to 1. Okay, so substitute theta square n plus 2, you get theta square over 3. So this one is theta square over n, which is 1. So that means variance theta head is less than the value that you get from Kramer-Rao lower bound. So our conclusion, this indicate that Kramer-Rao lower bound is not applicable for this question. Okay, since the variance theta head cannot attain the lowest value of your Kramer-Rao lower bound. That means variance theta head cannot attain the Kramer-Rao lower bound. So theta head in this case, theta head is not uniformly minimum variance unbiased estimator of theta. Okay, so that is your conclusion. Okay, so we have unbiased estimator and then we have the efficient estimator. So you need to check whether it satisfies the Kramer-Rao lower bound or not in order for you to conclude that this one is uniformly minimum variance unbiased estimator of theta. Okay, so next concept, the last concept, I just give you a definition. So any statistic that converge in probability to a parameter theta is called as a consistent estimator of the parameter theta. This means that the distribution of the estimates become more and more concentrated near the true value of the parameter being estimated, so that the probability of the estimator close to theta converge to 1. Okay, so this one is called as consistent estimator. When you have the limiting value and approaching infinity, theta head subscript n will approach to some value which is theta naught. So this is a consistent estimator. So if satisfy first definition, second definition, and the third definition, so you can conclude we have a good estimator. Okay. So last exercise, okay, I want you to do this one. If x is normal distribution, theta sigma square, which is your sigma square is known, okay, you show that the sample mean, which is x bar, is uniformly minimum variance unbiased estimator of theta. Okay, so try to do this one individually. We will discuss in our next class. Okay, so thank you all for today's. Okay, bye.